So thanks for being here. I think this might be a bit of a slightly different presentation than all the other ones I've seen. So I'm Marta Vanin. I am an incoming assistant professor at KU Leuven, which is a Belgian university. So yeah, I am with a university. I previously was in Professor Van Hertem's group at KU Leuven, where Professor Ergun also comes from. And we're a power systems group, essentially. My focus is on distribution networks. The group historically has a stronger transmission network tradition. And actually, Hakan did all the slides on the transmission parts that I'm going to present and couldn't be here to present them himself. So maybe all the details of the optimization on the transmission system, I don't quite know. But so I joined the group in 2018, and shortly after we were just starting to build open source software that we committed to maintain in the group. So we have an institutional GitHub account that by now counts quite a few members, quite a few repositories, not all are public, and quite a few contributors. I just wanted to give a shout out to Matteo and Veronica because they've helped a lot also establishing the ecosystem. And the question is, why as a uni do we need open source software for power system analysis? And one of the reasons is to engage the community, but also to be on top of new developments in technology, software, and market, which is now changing quite rapidly. And as academics, we want to be ahead of the state of the art. And this type of structure allows us to really rapidly prototype different type of models and solutions, which is quite handy. Also allowed us to sweep relatively easy between more academic-oriented research and industrial research. So I'm going to give a few examples. And yeah, it also is appreciated by regulators and decision makers that can actually have a look at the code. And we see that more and more we get positive feedback that our stuff is open source, even amongst other academics, because reproducibility is, of course, always desirable, but not very much often done yet. But we get a lot of encouragement about it. So just to give you a very short introduction about transmission and distribution systems. So the transmission system is the higher voltage part of the grid, and it connects large-scale power factory. Right now in Belgium, well, Northern Europe and other countries, HVDC are an important part of it. So distribution, direct current transmission lines, in a high voltage. But the system is historically AC, and so is also the medium and lower voltage power systems, which are then the distribution part, which is radially operated, whereas the transmission one is a mesh. And there are quite a few substantial differences between transmission and distribution networks that ask for then different solutions. One of them is the scale and the number of users connected to the system. There are a few in the transmission system. There are many, many more at the lower voltage levels. But for instance, a low voltage system, we could decouple a bit more easily because it's not meshed. Also, depending on how the networks are built, really the equations change a little bit. So some formulations, some simplifications that hold and are good approximations for transmission networks are really not in the distribution system. So what we really took inspiration from actually are power models.jl and power models distribution. So all our tools are built in the Julia language. And power models and power models distributions are from the Los Alamos National Laboratory, actually. They are the original developers. And what we use them for is really as generic power systems modeling libraries. They have different formulations. They host they've implemented what are the core constraints that are really underlying all our optimization problems. So Kirchhoff current law, really the basic physics law. We kind of import them from power model distribution, and we thought, yeah, okay, instead of just rewriting everything from scratch all the time, we'll take from them what we need and build on top of them. And one reason why we really liked power models is because it's based on Julia's JUMP, which is the mathematical programming package, which in turn is compatible with a lot of open source or also closed source solvers. So we can easily try different formulations with different complexity, linear, nonlinear, plugging the solver that can handle them. And yeah, as said, keep building on top of it depending on what the application or the project requires. So I'm gonna give shortly after this a carousel of everything we've been up to. Hopefully it's not too much less detailed information, but it's just to give a flavor of what we could do. Now, whether these tools are maintained or open source depend a bit on what projects they're in, what the IP requirements are, how big the team is, and how much we could retain senior team to keep maintaining the software that they've originally built during their PhD. But one nice feature of investing the effort in this is that typically even after the PhDs have left, if the code is open and it has been brought to a level of, let's call it decency to even make it open, then it kind of stays with the group. Which is handy in academia because, you know, PhDs get churned in and out at a kind of a fast rate. So what are the main goals and philosophy behind what we do? So it's still academic software. We do put the effort in the documentation, continuous integration, and to some of the repository, not all of them, we keep maintaining and developing on, those that we use more often, for instance. And yeah, it is used in industry, though. We prefer, or let's say we favor maintainability and modularity to performance. But because the Julia toolboxes that we use and the solvers that we use are quite performant, it's not like they're tragically slow either. So it's quite a good place to be for what we want to do. And again, the other advantages are we don't need to reinvent the wheel every time a new PhD comes in. And yeah, it's actually also handy to have these toolboxes as a benchmark in case some researcher wants to just try something completely different. They have at least a reference to benchmark to. So now start of the carousel on transmission system applications that we have been addressing. So because of the energy transition, which I don't think needs many introductions, there are a set of new challenges for system planning and operation. And one is that due to the increased power electronics, inverter-based resources, there's change in the system characteristics and limitations. For instance, there's harmonics are an issue, lack of inertia is an issue with respect to the large rotating synchronous machines that were the workhorse of the power systems traditionally. Then different type of uncertainties, more uncertainty in general. So how do we scalably handle these uncertainties, for instance, in renewable energy generation? And of course, we build decision support tool, I guess mostly for grid operators, although not only. And as such, also everything we do needs to comply to regulatory and market rules and interactions, which sometimes are straightforward to have as constraints. Sometimes you need to check back and forth, so it's not always very obvious. And yeah, with climate change, we also will see increasing weather events. I don't know if you know, but in Belgium, a few pylons were swept off just like a couple of months ago. So, well, there is more contingencies than expected. And the inertia is decreasing. But even though we do expect, for instance, that there's more risk for extreme weather, or even if we want to account for robustness towards all the new sources of uncertainty, maybe the worst case design approach is still a bit too costly. So there's still a lot of open research questions. And some of them are, for instance, can we leverage underground AC and DC transmissions, which is less exposed to weather events, but more costly because you need to bury the cables. Or how can we quantify techno-economic efficiency for underground transmission, also accounting for other sources of risk. So this is maybe a bit more technical economical, but it's still kind of an urgent question to ask, although it might not be the most fundamental sort of research. Then we have the operational coordination of onshore and offshore grids. The North Sea countries are really expecting to be hubs for massive integration of offshore wind power. And that, of course, can cause bottlenecks, congestions. It's something that wasn't done before. So again, there need to be decision support tools that help operators handle these type of situation, even, and then it gets a bit maybe looking towards the future for a time where we might have, I don't know, meshed HVDC grids in the North Sea, which can then share power between the North Sea countries, facing all then the sort of challenges that HVDC systems still have, such as protections and operation. So what we also try to think is towards more automated power systems. So right now, a lot of decisions are still made by the operator, more or less by heuristic, by going by what they've sort of always done and saw that it worked. And because of all these increased complexity, the decision processes really should be automated. There's some things like topological actions that the speaker before me was addressing. System operators just don't really have the tool in place to scale yet. And so there are still, again, there's quite an urgent need. We can develop some more tools that are close to what industry wants right now, but there's also then the possibility to use them for maybe more innovative research, such as how do we bridge the gap between the steady state simulations and the dynamic models? Do we have to iterate between the simulations, or can we incorporate some as constraints already? That's still something not fully answered yet. And in general, how do we go towards a more automated grid operation? So I'm going to give you just a quick example of how power models AC/DC looks like. So if you remember the slide, but maybe I'll just go back to the very beginning. So power models AC/DC is over here, is an extension of power models, which I think powermodels.jl does support models for DC lines, but did not have the converter models, for instance. So this has been developed a few years ago. And really, to give you an idea of the modularity, how this looks like, you would see that _PM are the pieces and bits that we imported from power models directly, and then we added, I don't know, AC branch flows, DC converter variables, and the relative constraints. And like that, this is how you would put them all together, and this is your optimization problem that will be built by Jump and then solved by whatever software, whatever solver is more appropriate. Now, because Julia also allows multiple dispatch, we can have the same problem and directly plug it into a different formulation, and which is also quite handy for writing and maintaining this type of software. So here you would have a type, and if it is abstract power models, that's maybe the more generic power model type. So for instance, AC power flow is the version of the equations that are used, but we could, I don't know, tell it, okay, do the same, but then linearize this and that, and then we see how faster it goes, for instance. So it's quite modular. You can remove the constraints you don't need or relax them. So it's really also very approachable for PhD students. Julia is also kind of nice to use. You write the equations down in the tool more or less like you would on paper, and still perform. It's still quite performant. So this is how all our Julia packages sort of look like if they do optimization. So I'm mostly talking about mathematical optimization models, so optimal power flow and variations on that theme. TNEP is transmission network expansion planning. There's something that the transmission team has worked on for quite a while now. And yeah, this is, for instance, one example of transmission network expansion planning. On the top figure, you see all the candidates, and then you find, given a future scenario with, I don't know, so much wind from the offshore turbines or the different loads that have been connected, it picks the most optimal or close to optimal candidates. That's pretty much what it does. And they have extended this sort of concept to FlexPlan.jl. FlexPlan was part of Horizon Europe project. So lots of partners. So they brought this in a bit of a step further. They now incorporate transmission and distribution grid in once. And you can try and address an optimal expansion planning problem as is, or other people have implemented decompositions, for instance, Bender's decomposition, or just decompositions between the transmission and the distribution networks and solved iteratively. And this is also the base of something Enside uses commercially. So this was, I haven't participated to the project, but I guess quite nice for the people who did, that this is actually, you know, used by a company as well. And yeah, as said, you can decompose the problem in transmission and distribution network expansion planning or not, and try different algorithms and see what's fast and optimal enough again, or where the trade-off is a bit. So again, there was an open source proof of concept. You can find it here. This is one of the packages that are still being improved on. And yeah, I think it includes, I've already pretty much said everything that is being included. A part of FlexPlan.jl is also optimal transmission routing.jl. Here, the grid constraints are relaxed, and it really just looks at separately for AC and DC lines, what's the shortest route really between 2 points that you intend to connect. So it's kind of a smaller thing, but it's something that needed to be done and then be added to the FlexPlan package. So another nice thing of using Julia is that it has its own package manager, and it's very, very easy to handle dependencies. And I don't know what software you usually use, but with Python, it's always terrible. Or there's always some dependency that just doesn't do it in the very beginning, and you need to spend time and fix. And this really does not happen with Julia. It's much easier to also understand where the errors come from. Moving on, we've also collaborated with some Australians. CSIRO is the Australian National Research Agency, and we developed a security-constrained optimal power flow that would solve fast enough for what the national energy market in Australia required, which was 5 minutes. And again, so the core of the tools is really mathematical optimization for most of them. So, but you can, of course, add pieces and bits that are not. And for instance, something that has been done here is a first filter on the contingency using some, I think, machine learning algorithm that then gives you a much smaller candidate space, so fewer binary variables, or well, fewer, yeah, a smaller contingency space. Then, yeah, as said, sometimes you just use it for more applied economical stuff. So CBA OPF just stands for cost-benefit analysis OPF. This is something that was done with the European Commission to see how we could benefit from having HVDC power flow control in the grid, for instance. So see, yeah, it's a cost-benefit analysis. So there's that. And there's also, I think, a bit of a thought behind it of seeing whether the grid code adequately incorporates the newer HVDC lines. So it also includes interfaces to the 10-year network development plan that NSOE has. It allows to aggregate and disaggregate zonal to nodal models, and also, I think, separate countries if you want to focus on one particular country instead of the whole European. These are a few of the results from the cost-benefit analysis. I think I don't really have the time to go into the details of this one, but in general, the conclusion was it does help to use inertia provision through HVDC. And we use the example of the Celtic interconnector, which is between Ireland and France, to showcase how much money that would be and how much benefits there is depending on renewable energy source generation in terms of inertia. So this was it for the transmission part. As said, it's not really what I do. I've helped a bit, but not a lot. I can still try to answer your question afterwards, though. Distribution system challenges and decision support tools is something that I've been more actively involved in. So one of the most maybe political questions are what is the hosting capacity of distribution grids at the moment? So how much PV can we have? How much can we decarbonize given the present assets before we really get into trouble? So we had an energy transition fund project from the federal government in Belgium, and our bit was calculate the grid hosting capacity. So I think other geography department looked into rooftop land availability, gave us that as input, and then given that, we developed a hosting capacity assessment tool. And the real question here was a bit, how do we handle the uncertainty of PV? The focus was on PV, because you could use a lot of Monte Carlo sampling, try out so many scenarios, but at that point it just doesn't really scale. So one of my colleagues implemented a stochastic power models.jl, which is also open source, and which uses polynomial Cauchy expansion to do this in more computationally scalable fashion. And yeah, calculate how much PV there can be hosted. So, however, that's kind of a planning problem, if you like. There's people who also talk about dynamic hosting capacity, looking a bit more at the right now hosting capacity given, I don't know, for instance, flexibility decisions that have been made. That was more really just a planning problem for us so far. But there's also operational problems, right? Because you have all these inverter-based resources. You have some assets that could be controlled or that do benefit from some automation, but they're not super many. And what really we have been working on a lot lately, or really what my focus was, is now that we do have finally digital meter measurements, how do we use them as part of these tools for better network management and operations? Because for so long, the distribution grid has been unobservable, so it was being operated in a fit and forget fashion. And really, for instance, unless a customer would call the utility to complain that their lights are out, they wouldn't really know. Now this is changing with a little bit of telemetry. But so we can tell a bit better how the grid is doing, have a bit more of an informed idea of what a future scenario could be. And some colleagues have been looking into how to optimally use the already existing assets, because network operators will have to invest so much because of all these new low carbon technologies that need to be integrated. I think here is a figure from an estimate of the Flemish distribution system operator that needed to adjust their grid investment plan by 4 billion over the course of 9 years with respect to previous estimates, because there's more heat pumps than they originally expected. And so optimal reconfiguration of networks is one of these examples. So modifying the topology to avoid congestion, increase hosting capacity, or also just to reduce the network losses if you want to capitalize on that. And this is one of the things where, for instance, we didn't just look into mathematical programming, but also meta-heuristic. But it was nice that the PhD student that focused on the meta-heuristics bit, so genetic algorithms, could benchmark this with little modifications of the tools we already had to solve it as a mixed binary problem. And then this was also sort of a planning problem. Now, because you have some telemetry, you could also think for the first time ever, really, you can monitor the grid. So we have implemented a state estimator for distribution systems. And really for that, we put a lot of focus in trying to capture the physics, the imbalance, the multi-conductor properties of the networks to avoid to add errors and as such optimally collate the network models to the data. And this taken into account also that, yes, there's more and more telemetry, there's more and more smart meters, but not all over the place, not all the time, not in real time. So one of the goals was to make these tools flexible enough to address these under-observed, if you like, scenarios. And this is also one of the packages that we are still developing. We've also tried to use it for slightly less conventional uses of state estimation. So yes, you can estimate the state of the grid, provided that you have an accurate enough network model and okay measurements. But state estimation also can help find out errors in the network model. For instance, you can see here this plot without going into too many details about what this is. Essentially, if there is an error in your network model, it stands out from the state estimation calculation, so you can think of adjusting it and improve the network model, and that improved network model the network operators can use also for optimal asset planning. It's just due to historical reason, connectivity is a bit uncertain, so network operators don't exactly know if you're connected to one feeder or the one slightly further. Yeah, we got real data from the network operator and also other in Europe. It's not just a Belgian problem, quite the opposite. Because the systems are so old, they've been not digitally recorded, and we see that oftentimes it's not quite what we expect that the connectivity is. So we've used this software in a bilateral collaboration with the Flemish DSO, also with the ImproCap project we recently started is if you know the Belgian funding schemes, it's a VLAIO project. And we're also looking into more and more this extension of the state estimator to find out, for instance, the phase connectivity of single phase users. That's also some of the parameters that are not really known in present grid, as well as estimating impedances of the cable. The impedance, the idea of the impedances that network operators have stored are in general quite off. And this has, of course, an impact, again, in your hosting capacity calculations, because depending on whether you over or underestimate what the impedance values are, you might be putting more PV than you actually could and now have to curtail, or the other way around, you're suboptimally using your network, you could put more PV. And it was quite nice, we could work with real data. So we got some from, again, because we're based in Flanders, we mostly work with the Flemish system operator. So these here are the output of the state estimation. They're a bit blurry, I'm sorry. And these are essentially the higher, the lower the confidence on the network model, and we split the data that they gave us in a training sort of data. It's not really training a machine learning problem, it's just trying to figure out from that data if there are errors, correct them, and then on a validation set, see how the state estimation objectives would perform, and you see that they consistently go down in different fashions for these 3 different feeders. But essentially, this gives us also some confidence on the fact that the models that we now have are better than what the network operator previously had. You can never know the ground truth, really, unless you dig the system out, which is not really possible. So it was quite nice, because if we do get a bit more confidence on how the network models look like, the network operator then can also be a bit less conservative in their hosting capacity calculations and, you know, hopefully get more low carbon technology in. Then, of course, everyone is talking about flexibility and dynamic operating envelopes, especially in Australia. So we're also looking into that, and the nice thing of having all these toolboxes that can account for network constraints in different fashions, we can already incorporate the network as a constraint for any flexibility schemes that we can think of. Because more and more people realize that if you just do something flexibility without caring about the grid, it sometimes actually exacerbate congestion. So yeah, you can either do your thing and check later if you cause congestion, or you can incorporate the network constraints directly. It's not always possible or straightforward, but with these things, we can look into that. And I think it's been a bit much already, so I would like to conclude with the slide that I actually showed in the beginning. These were the reasons that brought us a bit, I think, in the beginning to release open source code. And we see that, for instance, we now have external contributors to our tools, so other academics mostly. So it worked. I mean, it's always appreciated that somebody else uses their time to correct your bugs and stuff like that. That's nice. It's been very useful to get newcomers started, to not lose the work of PhD students that have left. And again, even if we have a project or a PhD student that decides, I don't care for mathematical optimization, let me do something else, they have something that they can then benchmark their tools with, because also, most likely, there is a reviewer that will ask for your paper if you have done all the due diligence. And yeah, they can use that to show that, for instance, yes, the mixed binary nonlinear version did not solve it all. So, and then as said, we did get quite some good reactions from other academics by our software being not only open, but also really documented and a bit reusable. And yeah, I think the structure that we used, which again, we really also got the inspiration originally from what the people at the Los Alamos lab did, really suited well the work so far, because you can use it for lower TRL, but also higher TRL. Maybe it's not really production grade stuff, but you know, it's performant enough to convince industry that maybe they can fund you, or that it is a valuable set of capabilities to have. And the last slide is just QR codes. So I stop here and answer your questions if you have any. Yes?
It was very interesting to see your use cases. A question that's not so much like power system oriented, but more sort of like usability by the community. Have you ever had any pushback for using Julia in a world that's more like sort of Python oriented? Like, were people struggling with that, and were people in the industry like familiar with that language, or was it considered to be more sort of like niche academic in your experience?
Yeah, it's quite a relevant question. So as I said, I'm with the uni, but we're also part of Etch-EnergyVille, which is a consortium where the Belgian, or no, Flemish research center, Vito, is part of. They do a bit more higher TRL stuff. They've used Python always, and definitely having our tools as part of their tools. Certainly in the beginning we had no idea what we were doing, so the integration was a bit painful. You can integrate them though. There's just, you need to probably build the expertise a bit in the group, because this is not really research, it's more implementation. But we have a couple of instances where we have their larger Python pipeline that I've been building for so many years, and now a little bit of that actually calls Julia under the hood and runs stuff.
So they were not reluctant to use something they wouldn't understand as an integration? Like that was not a problem?
Not really, because the alternative was not having it. I guess if they would have a comparable Python alternative, for instance, yeah, maybe they would have used that and maybe even sacrifice a little bit of what we could have done. But because there's just no such thing, yeah, they have welcomed it. And yeah, in the beginning, again, we didn't really know how to do it, and now we know a bit more. So yeah, it's yeah.
I have a question. Do you have any links to powersystems.jl by Unreal?
We have never, or I have never used it. I think there's some people in the group that do, but so we never really developed anything on top of that. I think they have been used there maybe better for dynamic simulations, I think. Although, or yeah, and larger scale computations, but I've never used it. There's people who did, but we haven't developed anything similar, so yeah. Yes?
Do you use some open standard for the data that are needed for this simulation, or it's a specific academic vision of?
So because we have power models as a dependency, and we try to then use something which is compatible with power models, which then is a Julia dictionary. Power models and power models distributions come with MATLAB parsers, so that's kind of possible out of the box. OpenDSS parsers, which is really the format, I think, in the distribution system calculation community, at least the ones that use open source tools. And otherwise, I think you'd have to write your own parser. No, or maybe I think for the transmission, there's another bunch of well-established formats. Again, for PSCAT maybe, PSC. Those are also already have parsers. For distribution networks, OpenDSS is really pretty much the only consistent thing there is, and then every network operators has their own data in their own format. So for those, we would anyway have to write the parsers. Yeah. Yep. Okay. So pretty much right on time. So if there's no more questions, we can have coffee.